All right, buckle up, because today we're diving into some seriously weird physics. We're talking about the possibility that space and time, those things we always thought were kind of fixed and unchanging, well, they might actually exist in multiple states at once.
Yeah, it's a real head scratcher.
Yeah.
And it all boils down to this question. Can space-time pull a disappearing act? Like,
Yeah.
can it be in two places at once?
And we're not just talking about some abstract theoretical stuff here. This has huge implications for our understanding of gravity, especially at the quantum level, which is like the ultimate frontier of physics.
Right. It's like we're trying to listen in on the universe's deepest secrets, the rules that govern reality at the smallest possible scale.
So to guide us on this deep dive, we're going to be unpacking some fascinating new research from a recent article. And let me tell you, it's some pretty mind-bending stuff. Essentially, we're going to try and wrap our heads around the possibility of actually observing the quantum nature of gravity in a lab.
Which is a pretty big deal, because for decades, scientists have been grappling with this fundamental clash between two of the most successful theories in physics, Einstein's general relativity and quantum mechanics.
It's like these two theories, which both work incredibly well in their own domains, are speaking completely different languages.
Yeah. Exactly. You've got general relativity, which is like the king of the cosmos, explaining how gravity governs the motion of planets, stars, galaxies, the whole shebang. But then you zoom in to the subatomic world, the realm of electrons and quarks, and suddenly it's quantum mechanics calling the shots. And these two theories, they just don't play nicely together.
So what's the problem? Why do we even need these two theories to get along? Can't we just keep them separate and call it a day?
Well, it's not that simple. There are places in the universe, like inside black holes or at the very moment of the Big Bang, where gravity is incredibly strong and quantum effects become significant.
So like the universe's ultimate mosh pit, where everything's so extreme that our normal rules of physics just kind of break down.
Pretty much. And in those extreme situations, we need a theory of quantum gravity, a theory that can bridge the gap between the macroscopic world of stars and planets and the microscopic world of atoms and particles.
So are there any promising candidates for this theory of everything title? Any theories out there that might actually be able to unify gravity and quantum mechanics?
Well, there are a few contenders, each one stranger than fiction. One of the leading candidates is called loop quantum gravity, which suggests that space-time itself, the fabric of the universe, isn't smooth and continuous, but is actually woven together from incredibly tiny loops.
Okay, I'm picturing like a cosmic chainmail, tiny loops all linked together.
Exactly. And then there's string theory, which is a whole other ballgame. String theory proposes that everything in the universe, and I mean everything, is made up of these tiny vibrating strings.
Okay, so we've got loops and strings, both trying to explain the fundamental nature of reality.
And the wild thing is, both of these very different theories seem to agree on what we should see happening at the energy levels these crazy new experiments can actually test.
So how do we actually test these theories? I mean, are we talking about building a giant particle accelerator in space? How do you even begin to experiment on something as fundamental as space-time itself?
Well, it's not easy, that's for sure. But the key to unlocking the secrets of quantum gravity might lie in a rather elegant concept called interference.
Interference. Like noise-canceling headphones use interference to block out sound waves, right?
Exactly. It all comes down to waves. And believe it or not, interference has played a crucial role in our understanding of the quantum world for over a century.
Yeah, I had no idea it had been around that long.
It has. Back in the 19th century, long before quantum mechanics was even a glimmer in a physicist's eye, a scientist named Thomas Young conducted this really simple but ingenious experiment with two slits in a beam of light.
So like shining a flashlight through two tiny holes, what did that tell us about quantum gravity?
Well, Young's experiment, which is now famously known as the double slit experiment, was revolutionary because it proved that light, which we often think of as particles, little bundles of energy, also behaves like a wave.
Okay, so light is a wave, but also a particle. It's both at the same time. My head's already starting to spin a little.
Welcome to the world of quantum mechanics, where things rarely make sense. But that's a whole other deep dive. For now, just remember, light is both a wave and a particle. And Young's double slit experiment showed us that when light is shown through two tiny slits, it creates an interference pattern on the other side, with bands of light and darkness, just like the ripples in a pond. And that discovery opened up a whole can of worms because it got physicists thinking, well, if light, which we once thought was purely a wave, can act like a particle and show interference, could the opposite be true too? Could particles also act like waves?
And what did they find? Can particles pull a double duty act too?
Turns out they can. A few decades later, a physicist named Louis de Broglie proposed that all matter, like electrons or neutrons, should also have wave-like properties. And if they did, we should be able to observe interference patterns with them, just like Young did with light.
So it's like the universe has this weird sense of symmetry. If light can be both a wave and a particle, then particles should be able to act like waves too. And did de Broglie turn out to be right?
He was. Later experiments with neutrons proved his hypothesis, confirming that particles, those tiny bits of matter, can indeed act like waves and produce interference patterns.
Okay, so we've got light and particles, both pulling double duty as waves and particles, and both creating those telltale interference patterns. So how does this all tie back to gravity? Could we use this interference effect to actually see gravity behaving in this quantum way?
Now you're asking the million-dollar question. And that's exactly what we're going to explore in the next part of our deep dive.
So we're talking about literally seeing space-time, the very fabric of the universe, in multiple states at once. That's like saying my comfy chair could be both here and over there at the same time.
It does sound like something out of a science fiction novel, doesn't it? But to understand how it might be possible, let's try a little thought experiment. Imagine we take an object, something with mass, and we somehow manage to put it into a quantum superposition. Now remember, superposition means it exists in two places simultaneously.
Okay, I've heard of this. It's like Schrodinger's cat, right? The poor feline is both alive and dead until we open the box.
Exactly. Now, let's bring gravity into the picture. According to Einstein's theory of general relativity, any object with mass warps the spacetime around it. The heavier the object, the more warping it causes. It's like placing a bowling ball on a trampoline. It creates a dip, a curvature. So if our object is in two places at once, it's actually warping spacetime in two different ways at the same time.
So space-time itself, the very fabric of the universe, is in a superposition of two shapes. My mind is officially starting to bend.
Here comes the truly ingenious part. Imagine we shine a beam of light past this object that's in superposition. If gravity behaves classically, the light would only interact with one of those space-time geometries, the real one, and travel along a single path.
Right. It's like the light only sees one version of reality, one shape of space-time. But what happens if gravity is playing by the rules of quantum mechanics?
Then things get really interesting. If gravity is indeed quantum, the light would actually travel through both space-time geometries simultaneously, as if it's riding two waves at once. It's like the light is taking a detour, experiencing two realities simultaneously.
Okay, I'm trying to visualize this. So the light wave splits, travels along two different paths, each shaped by a different version of warped space-time. And then what? What happens when those light waves meet up again?
They interfere with each other, just like the waves in those noise-canceling headphones or the ripples in a pond. These light waves, having traveled through two different space-time shapes, would recombine at a detector. Now, here's the crucial part. If we see an interference pattern, those characteristic bright and dark fringes, it would mean the light was influenced by TWO spacetime geometries.
Wait, so just by looking for this interference pattern, this fingerprint of the quantum world, we could prove that spacetime itself can exist in multiple states at once. That's huge.
It is huge. But pulling off this experiment is also incredibly difficult. There's a catch, you see. To have a noticeable effect on spacetime, we need a fairly massive object, and that's where things get tricky.
What's the problem? Don't we have giant telescopes and powerful particle accelerators? Surely we can find something massive enough to do the trick.
It's not just about size. The problem is that massive objects tend to decohere very easily. Their quantum behavior, that ability to be in multiple states at once, gets washed away by interactions with the surrounding environment. Think of it like trying to balance a pencil perfectly on its tip. Any tiny vibration, a breath of air, can topple it over. Massive objects in the quantum world are incredibly delicate like that.
So we need something heavy enough to warp space-time in a noticeable way, but small enough to maintain its quantum superposition, to stay balanced on that tip, so to speak. It's like trying to find a needle in a cosmic haystack.
It's a daunting challenge, but physicists have identified a possible sweet spot: the Planck mass.
The Planck mass, what's so special about it?
The Planck mass is incredibly small, about 20 micrograms. To put that in perspective, it's roughly the weight of an eyelash.
An eyelash, that's tiny.
It is tiny, but in the quantum realm, that's a heavyweight. It's at this incredibly small scale, to the scale of the Planck mass, that the effects of both gravity and quantum mechanics become equally important.
So it's like the meeting point of these two titans of physics, the quantum and the cosmic. So what you're saying is we need to wrangle objects the size of eyelashes, get them into superposition, and then see if they create interference patterns in light. It sounds like we're pushing the very limits of what's measurable.
It is pushing the limits, no doubt. But the progress that's been made is astounding. Scientists have actually managed to put objects on the order of the Planck mass into superposition. It's an incredible feat of engineering and ingenuity.
Seriously, we can do that now.
We can. But of course, there's a but. The separation between those two superposed locations, at least for now, is still far too small for us to see the gravitational effects we're looking for. Imagine trying to measure the width of a human hair with a ruler, meant for measuring the distance between planets. It's a matter of scale.
Okay, so we've got our Planck mass eyelash, and we can put it in two places at once, but those two places are so close together that we can't actually see the gravitational effects. So what's the plan? How do we bridge that gap? Do we need to invent a whole new kind of measurement tool?
It's a multi-pronged challenge. One issue is the wavelength of the light we typically use in these kinds of experiments. To be affected by the gravity of these incredibly tiny masses, we would need light with an unbelievably small wavelength, something on the order of 10 to the power of negative 32 meters. That's smaller than anything we can produce.
It's like trying to read a microscopic inscription with the naked eye. You just need a more powerful lens to even see it.
Exactly. The wavelength of light needs to be small enough to interact with those minuscule warped regions of spacetime. Otherwise, it just passes by without a blip. Now, some researchers are proposing that instead of light, we use another quantum mass, a different particle, as our probe.
Okay, so instead of shining a light on our superposed object, we use another quantum object as our measuring stick. And what would be the advantage of that?
The advantage is that the strength of the gravitational interaction depends on the mass and speed of the probe. The heavier and slower the probe, the stronger its gravitational interaction with our superposed object. Think of it like this. You'd need a much heavier bowling ball to make a noticeable dent on a trampoline than you would a ping pong ball.
That makes perfect sense. A heavier object has a bigger impact, so we could use that to our advantage. But we still haven't solved that other problem. The separation between those two superposed locations being infinitesimally small. Any ideas on how to tackle that? Or are we stuck with our cosmically short ruler?
This is where things get even more mind-boggling, even more deep dive worthy. There's a completely different approach gaining traction among physicists, one that relies on a truly bizarre phenomenon called entanglement. And if you thought superposition was strange, get ready to have your mind truly blown, because with entanglement, we're talking about spooky action at a distance.
Entanglement. Okay, you definitely have my attention. This is why I love these deep dives, always venturing into the unknown. So tell me, what is this entanglement idea, and how could it help us prove that space-time itself can be in superposition?
All right, so picture this. We've got not one, but TWO of these Planck mass particles, right? Each one tinier than an eyelash, and each one doing this quantum disappearing act, existing in two places at once.
Okay, two tiny eyelashes, both in superposition.
Got it.
Yeah.
So what happens when you get these super small, super strange objects entangled? How does that show us anything about space-time being in multiple states?
Well, remember how we talked about mass warping space-time? Well, with two superposed masses, the distance between them becomes superposed too.
Wait a minute. You're saying that the distance itself, the space between these particles, is also in two states at once. That's like saying there are two different lengths of a ruler existing at the same time. You got it. It's like having multiple maps of a city, right? Each one showing slightly different street layouts, all superimposed on top of each other. And here's where the really trippy part comes in quantum entanglement. See, those particles we've been talking about, they're not just sitting there. They oscillate, they vibrate at a certain frequency, and get this, that frequency is affected by gravity.
Okay, so stronger gravity means a slower vibration. It's like those particles are tiny clocks ticking away at different rates depending on the gravity around them.
Precisely. And since the distance between our entangled particles is also in superposition, they're experiencing different gravitational forces simultaneously. This difference in gravitational pull creates a measurable difference in their oscillation rates, which tells us they are entangled. Their fates are intertwined in a way that classical physics simply cannot explain.
So we're not even looking for interference patterns anymore. Instead, we're looking for this spooky action at a distance, this entanglement between particles, as evidence that space-time itself can be in two states at once.
Exactly. The theory predicts that we'll only observe this entanglement if the gravitational field itself is in a quantum superposition. If the gravitational field can pull off this quantum trick, then space-time can too. It's like these entangled particles are acting as our supersensitive gravity detectors, giving us a glimpse into the quantum realm.
Okay, so to sum it all up, we've got these two mind-blowing approaches to potentially proving that space-time can exist in multiple states at once. We can try to catch it in the act of being superposed by looking for interference patterns created by light or particles passing through warped regions. Or we can use entangled particles, these spooky quantum clocks, to see if gravity itself is playing by quantum rules.
And the truly exciting part is that either way, we're poised to make groundbreaking discoveries. If these experiments succeed, it would be like turning science fiction into science fact, confirming decades of theoretical work, and opening up entirely new avenues for exploring the universe at its most fundamental level.
It would rewrite physics as we know it. And even if the experiments don't confirm quantum gravity, we'll still have learned something profound about the nature of gravity in the universe. It's a win-win for science.
Absolutely. Either we confirm some of our wildest theories, or we stumble upon something even more unexpected, even more mind-blowing. That's the beauty of scientific exploration. The journey is just as important as the destination.
Well, folks, there you have it. We're on the verge of potentially witnessing the quantum nature of space and time directly, which is about as mind-blowing as it gets. A huge thank you to our expert for joining us today and for illuminating this incredibly complex topic. And for all you listeners out there, keep those questions coming and keep exploring the universe within and the universe all around us. Until next time, this is The Deep Dive signing off.